Hello everybody! I hope everybody's having a wonderful day. So I'm going to pick up where we were last day. So I finished up last day talking what we're going to use as kind of our working definition of a data structure. So the collection of values or objects, which is called a data type. Remember we established this last day. And a set of operations on those values or objects. So you can think of the data structure as a concrete representation of an abstract data type. AKA its implementation. So, keeping this simple, I'm going to give you some examples of data structures. So, example, you might know strings. So, a string, for example, would be considered a data structure. You might be aware of an array. Array is a example that's rather fundamental and quite simple. You might know of a linked list. A linked list would be a data structure. So, I want you to think a little bit about what things like this might look like if you were to try to formalize them a little bit more. Because strings, for example, have a whole bunch of operations. In something like Java, they have a bunch of different methods. An array, you can think of them as you can access given positions, you can set values, and you allocate a contiguous piece of memory. In contrast, you have in a linked list, insertions, removals, and you should be aware of some algorithms for performing those operations on a linked list. Like I said, the definition for our data structure is really broad. So don't look at this as something like, oh, this is extremely formal. This is something that is, in fact, pretty broad. So just to give you an example of what I mean by this, and I just really want to emphasize this. The data structure addresses this. The big point about this is it addresses the how. So it addresses the question how. So the abstract data type gives you the specification of our data structure. Its actual implementation is the answer of not just the what, but also the how you actually do it. So what I mean by this is how each operation is performed. And of course, how the data will be organized. So when I say how it's going to be organized, this is a little bit more concrete than what I'm saying, oh, I give you a mathematical abstraction or model of the data structure. This is actually telling you like how I'm actually going to concretely do it. I'll show you an example in a moment and how each one of these is performed. So those are kind of like the two big things. But the biggest part is this, what strays this from the definition of an abstract data type is the fact that you actually are implementing the operations. That's the big part here. Because in an abstract data type, the operations are only accessible through an interface. Now, you might ask, oh, well, Dan, what's this interface business? It seems rather superficial or strange. Maybe I don't know what I might be thinking about this whole idea. Okay, so I want to give you the big picture. So you might look at this and say, okay, well, that just sounds like I'm adding an extra layer on this. It's actually quite deliberate. So if I think about abstract data types, so I give you some specification of a data structure, and at the same time, I also want to have some operations. You could think of this whole process of trying to implement the data structure as a problem statement, where each one of my operations are a problem that I need to solve. So we'll talk more about problems in a bit. But the big idea I want you to think about is that you can look at the data structure like, okay, here's this thing I want to implement. How am I going to do that? That's the problem. So it has two purposes. One, to conceptualize and somewhat formalize the actual thing we need to implement, like a problem which needs to be solved. So in this case, the operations that need to be implemented to maintain and control this data structure. Secondly, it actually operates as a nice conceptual way of modeling. So when I look at this and think about, okay, well, I have to implement the operations, and once I have that, then I can say my thing is that thing. Like if I implement all the operations of a stack and I follow its specifications, then it's a stack by definition. The big thing I want you to think about is, okay, well, if I give you one possible data structure for, say, for example, a stack, there can exist other implementations of a stack. So each one might have their own drawbacks or pros or cons. And the whole idea is you want to try to find the most efficient way you can implement that data structure. So it functionally operates like I give you some specification, and now there can exist many different implementations of that data structure. So as long as you implement its operations correctly and you follow its specifications, then you can say it's that it's in fact that data structure. It is in fact a stack. The other thing more functionally when it comes to programming, the whole idea is that once I have this abstraction away from thinking about code and things like that, then I can talk about a stack and talk about how I might implement that. But functionally in a language like Java, if I create a Java interface, for example, what I can do is I can specify all the operations and what this should be. So for example, if I want to declare what a stack is as an interface, what I could do is specify all the operations, and you're only allowed to call yourself a stack unless you implement all of my operations. So that's what an interface in Java might look like. In contrast, you can also think about interfaces more broadly. For example, I can have two objects, and I can say these two objects are comparable if the only thing they operate or functionally implement is a method called compare to. So I could take these objects, and if I could do that, then I could call it a comparable object. Same idea. So you're going to find this is quite natural in an object-oriented programming language like Java. We've also encountered this possibly with C++ and something like classes. In particular, an abstract data type would be natural to implement using an abstract class. So where you would specify the methods, but you don't actually implement them. You have to inherit from it, if we're talking about inheritance. So hopefully this gives you an idea. So remember just those two big things. One, the abstract data type allows me to then think about each data structure like a possible implementation of the ADT, and thus meaning that I can implement each one and give you different implementations for that ADT, each with their own possible benefits or drawbacks. Sometimes you'll find that you'll find the best data structure for the best suitable application you might have. Other times, you'll find that there's very much trade-offs. We're going to find with some of the data structures we're going to see in this class that there's going to be trade-offs. And the second thing, of course, is it operates very much like in this idea of abstraction. So I want to take away, I want to strip away any kind of implementation-specific details from my definition of an ADT, so that if I declare something as an ADT, that I don't have to know how the inner workings actually operate. Instead, I can abstract all those details away and I can just use my data structure as it's being declared with that name. So if I have a stack, I don't have to worry about the inner workings of my stack, how I actually implement the operations, and how I organize the data. I just need to worry that it's a stack. Anyways, so just keep in mind those two things. So if you're looking at the big picture and then stacks, those are kind of the big two takeaways here. So I'm going to do an example. So just following with our example of a stack, I should make aware that, as I kind of said, each one of these operations, each operation is an algorithm. Now, for the sake of simplicity, because you probably are aware of these things, if not, you'll find that the way I treat it should be pretty basic. I'm going to keep things simple. So let's consider a stack data structure. And I'm going to implement it. So I'm going to be implemented with with a linked list. Now, if you're not familiar, remember a linked list, you may know this as a linked structure with a linear ordering. So what I'm going to do is I'm just going to draw a picture of what this is going to look like. So first I'm going to have the head of the linked list. I'm just going to call that top. So the head of the linked list refers to the first node of the linked list. And there's going to be two attributes in each one of the nodes of my linked list. So this is just called a node. The node there. And there's going to be two attributes. Some data, which is going to store my elements, and another attribute called next, which is going to be a reference or pointer. You're going to find in Java, you're going to use the word reference a lot because that's kind of a Java-ism in contrast to a pointer. I'm just going to refer to it as a reference just for simplicity, but I'll use the word reference and pointer interchangeably. So I could have my first node in A as the element. Then I'm going to have my next node, which is going to be referred to by this right here, which is going to store the address for which the next node is located in the heap or heap memory. So I'll call it B. Then the next node, I'll call it C. And its next reference is going to point to D. Now, D is going to be the last node in my linked list. So there's going to be nothing that's going to be referring to in this next attribute here. So I'm going to refer to this as nil or null. So that means it's just not pointing to anything other than null. So you should be familiar with this. This is a linked-based implementation of a stack. This one's actually quite nice, but I'm going to describe to you how I'm going to implement the two operations I said I was going to support. Keep in mind, you can do it for the rest as well, but I'll just describe it for here. So I'm going to have two operations I'm going to describe. So I'm going to describe push first. So what I do when I do a push, okay, let me remind you. So remember, when I perform an insertion into the linked list from the front, what do I do? What I do is I create a node, so a node object. I put my data inside it, so I assign the data to be what I need to insert. And then I make the next reference to be what used to be the front of the linked list. So I do a little bit of surgery to get it in here. So fortunately, insertions at the front of a linked list is rather straightforward. So I'm just going to describe this in words. So create a node containing element E as its data. And insert it at the front of the linked list. So I'm not going to worry so much about the details here because you should be aware of how to insert a node into a linked list. So just reminder, I haven't explicitly wrote it down here. However, normally when you're writing out an algorithm, you want to do that, but this is just mostly me trying to recap something for you. So remember, when I create the node, I have to make sure I specify the next reference, which would be the original version of what top was, before I reassign the front of the linked list to be this node containing A. So that's push. Pop is pretty straightforward. All you have to do is you're just going to remove the first node in the linked list. And return its data. And now I must remember, so I'll return the first node as data and just say null otherwise. Right? Remember we said that if the linked list is empty, then what I would do is I would just simply, okay, well, if there's no nodes, then it's about the equivalent of me having no plates, like in my analogy before. So I should return null, because there's nothing. Now the great thing is that you should be able to easily check this by just simply looking at, okay, let's top. Well, when there's no nodes in it, top is going to be null, so you can just easily check that. If top is equal to null, then you just simply just return null, right? Pretty straightforward. Okay, so those are my two operations. So you'll notice that this is a implementation of a stack. So this is some implementation of a stack. So for example, I have my 4 plates again. Notice that if I have my 4 plates, imagine the different colors represent A, B, C, and D. What I can do is imagine I start off with an empty stack. What I would do is I perform my push. Say push D is the yellow plate. So I start off with this one here. Now, the plate itself is the element. So the node is containing this plate. So this is what element is. Likewise, this could be C. I push that onto my stack. So now I will have 2 nodes. Then the pink plate, we'll make that B. We have 3 plates. If I pop off this, I return back the plate. I don't return back the node, I return back the plate. And lastly, I'll push that back on there because it's fun. And then I'm going to push the green one, which is A. So there's a stack. Seems pretty nice, right? Okay. So where are we going to go from here? We're going to start talking about problems. So this should give you a general gist of what a data structure is. Now, to make the rest of this picture come and complete, before I talk about algorithms, I need to talk about what a problem is, specifically a computational problem. So I'm going to give you a broad framework to talk about problems. And you'll find that in this course, we're going to talk about problems in this fashion. It's very common to describe problems in this way in computer science. So just be aware of that. Because in your first year, you may have thought about problems in somewhat of a less concrete way. You're going to find that I'm going to model problems in a much more formal way, such that I can tell you definitively if your algorithm is correct or incorrect. But before we talk about algorithms, I got to talk about problems. So hopefully we're all good so far. So let's talk about problems. So problems are all around us. Just waiting to be solved. Okay. So in CS, you will encounter many different kinds of problems. Some quite fundamental, to daily life. Daily, we'll go with daily. I have in my notes, I say every day. We're just going to go daily. I intend the same thing here. So, problems, you're going to I'm going to give a broad kind of look at what a problem is. The type of definition I'm going to give you is a function problem. So we'll talk more about what that means in a moment. We're going to see a couple of different kinds of problems in this course. There's some that are, I would argue, even more fundamental than the ones I'm going to show you here that actually will be seen in the third year. So those would include examples like decision problems. So I'll introduce a problem just to give you an example of what I mean by a problem. So we'll talk about a problem I'll just refer to colloquially as the search problem. So the search problem is given a set S of elements and an element, which this I'll typically call the key quite often. Element X determine whether X is in S. This seems pretty straightforward, right? I give you some collection of elements, S, and I give you some key, X, and I just want to know if X is in S or not. Typically, how we're going to use this is I'm just going to have to report back the location of X, if, say, the data is in fact ordered. More broadly, if I get a set, your job is just to tell me if it's there or not, and possibly return it. So I want to give you some examples of how you could encounter the search problem. Just because I keep saying that this stuff's so fundamental to daily life that I should probably give you some concrete examples of what I mean by this. Okay, so here are just some examples of things that the search problem, so here's some applications that you need to think of. And sometimes you just need something a little bit more concrete to play around with as opposed to seeing something a little abstract like this. You'll find the more you encounter problems, the more you'll be inclined to look at things more like this, where you, instead of thinking about a very concrete problem where you're given some program specifications, you'll instead think more in this more general way. So then you have to ask broader questions. For example, okay, what data structure should I use to model this? What algorithm should I use? Is my algorithm correct? These are a lot of things you're going to think more about as the more you kind of pursue into a study of computer science. You'll think of things in a lot more of it's a much more formal or mathematical way of thinking about problems. So that being said, we always want to define problems like this have to be very exact. There can't be really much wiggle room what the problem is, that's where really you're going to run into a lot of issues around practice. So that's its own right a very interesting topic. So here's some examples of natural applications. So if I give you variables in a program, this would be S, and a name of a variable will be X. So imagine I give you a program and I have a set of all of the variables. I want to know if the name of my variable that I want to know, X, is among all those variables. So that seems pretty nice. How about student records? You can think of a big database where you have a bunch of student records. And I want to know if there's a student that has a particular student ID. And the student ID would be the key X. So that one seems pretty natural. How about a web host? So the web host names and a URL. So you want to just check and see, hey, look, is this URL part of the web host names? Yes or no? Okay. This brings me to what I'm going to describe as a computational problem. So here's kind of the working definition we're going to use. A question or statement that requires solving. See, like I said, it's going to be requires solving. So more specifically, now this is the part that actually matters in our definition here. A computational problem is an infinite collection Now, it's worth noting that if you're solving a problem with only a finite number of instances, you can just ignore this infinite part. Just usually interesting problems have an infinite collection of what we're going to refer to as problem instances of possible problem instances. Problem instances. So now, I deferred the definition now into a problem instance. I have to tell you what that means. So here's what I'm going to refer to as a problem instance. Each problem instance which I'll abbreviate as instance, of a problem has inputs Now, very often you'll find that I use the phrase input instance to refer specifically to the inputs. Input instance. Just to get around the whole issue of saying singulars or plurals. Input instance. And upon being solved, has a solution. Okay. So just to reiterate this definition, because this is an important definition. So a computational problem is a collection of possible problem instances. Each problem instance of a problem has inputs, which I'll refer to as an input instance. So if I just give you a problem instance, usually you'll find that people will use the phrase input instance and problem instance and instance like synonyms when they're talking about just the input. I'm just going to use it a little bit of a broader way just to describe that the instance has inputs and it has a solution. So the big thing here is I want you to kind of visualize this. Now this sounds like a mouthful. It's like, what the heck do you mean by an infinite collection? That seems very strange. Now, like I said, if you're working on a problem that does not have an infinite collection of instances, guess what? You could just ignore that part that talks about infinite. But usually instances that problems can be considered as a set of possible inputs over an infinite collection. So even of the one, if you're only considering a finite number of instances, it doesn't make any much of a difference because it's possible over this many elements in such a collection. So I just want to give you a picture what I mean by this. So here's a picture. Okay, so this is my problem. And in here, all of here, I have my problem instances. So each one of these is a problem instance. So the problem consists of all these problem instances. So normally when you talk about the problem instance, it's a set of our inputs, called an input instance. And each one of these will have a solution. So when you talk about the problem instance itself, it consists of the inputs, but each one has a solution. So naturally, when you think about a problem, you got to keep in mind that you have to consider all the problem instances. So I'm just going to reiterate this with an example. So just a few things. We will assume the problems are well defined. Now, you might not know what that phrase means. If you know things about functions, you might know what that means. So I'm just saying, basically, that each problem will be defined so each problem instance can be assigned values to their parameters or inputs. Such that there is some solution as prescribed by the problem. So what is this saying? When I mean well-defined, I just mean that for each one of these problem instances over there, it has parameters. But you should look at each one of these as a particular assignment of values to the inputs, such that if I pulled off one of these, I can feed it to an algorithm to solve it, which I'll talk about in a little bit. So either today or next class. So, just as an example, I'm going to consider the problem of sorting. So this is a very basic variant of sorting, but it's pretty fundamental. So given an array A of n integers, sort A in non-decreasing order. So this just means, if you're not sure what non-decreasing means, just look at the numbers. It's such that they're never going down. Like if I look at the numbers, they only stay the same or they go up in value. They don't dip down. So we'll just know this as smallest to largest. So if I give you the sorting problem here, now you'll notice that I deliberately didn't phrase it in the way such that my definition kind of fits. So I want to kind of help you identify what the input instance is and what a solution to this problem would look like. Because the way you want to look at problems like this, now keep in mind not every problem will look like this, but you'll find that the problems that usually computer scientists tend to be interested in, at least traditionally, they will normally have a particular kind of input-output type form to them. So I give you something, your job is to produce output that solves the thing that you gave it. Very simple. So here's an example of what I mean by this. So here's a problem instance. So when I refer to the problem instance, usually I'm referring to the inputs of that particular case. So the input instance. The input instance. Here's an example of the input instance. There's array A, and it's an array that looks like 1, 2, 1, 3, 5, like this. I'm just using the square brackets here. I could easily make them round or angle brackets, but I'm not going to worry too much about being overly formal at this stage. Now, if I give you this array A, by the way, what's n here? What would n be? 2, 3, 4. Yeah, 5, right? N would be 5 here. So the way you could characterize this is I give you an array and I give you an integer. But for the sake of simplicity here, I'll just imagine I give you an array A. You can determine what the length is. Just for simplicity here. Keep in mind, remember, I can formulate the problem. I can formulate it and I can try to solve it. There's going to be many equivalent formulations of the same problem, so just be aware of that. Just read what somebody's telling you what they're trying to solve carefully every single time. You should never look at this type of problem solving as, oh, it's just like a one-fits-all kind of solution. Just think about every problem like it's its own case that you should consider very carefully. What's the solution to this? Okay, well, all I have to do is I need to return A in sorted order, right? So what would that look like? Well, it'd just be A, or I just sort the numbers from smallest to largest, right? 1, 1, 2, 3, 5. See, that's not too bad. So when you look at each one of these dots, there will be an array, A, of length n, for some n. So this over here can consist of a whole bunch of instances, each arrays of different lengths with different numbers in them. So that's why I say it's an infinite collection of problem instances, is because there's no real cap on how many can be in here from some finite level. Each one of these is prescribed on a finite level. So each array has a length n and is one input to the sorting problem. But however, there can be as many, there's tons of these arrays, right? There isn't just some cap on how many possible arrays there are in this abstract way of thinking about things, right? So the big point I want to take away from this is to exactly solve a problem. To exactly solve a problem requires solving every problem instance. So I give you a problem instance. Remember, that's just the input instance. So I give you that, and your job is just to solve that problem instance such that it matches the solution. Okay? That's not too bad. Now, one point I need to get to before we really start talking about algorithms is the notion of something called input size. Now, it's going to sound somewhat technical, but I assure you it's really not that bad. But it's something very important we need to be aware of. Now, I want to, before I get ahead of myself, I want to kind of look at this picture here. So I told you that each problem instance is given to you as this input instance, and each one has a solution. Now, before I can even attempt to solve that problem instance, I should be able to take this input instance, encode it in some language a computer could understand, and then feed that to my algorithm. But what exactly is an array like this with a bunch of numbers in it? Well, really, it's just a sequence of bits, right? Because in my computer, I actually have to take and encode that into a bunch of bits. But what does that mean? Well, that means that I have each one of these arrays actually use an encoding or so-called bit string. It's just a bunch of zeros and ones, or whatever choice of encoding scheme you want to use. And what you'll notice is that a lot of times in algorithms, the longer this bit string is, the longer your algorithm is possibly going to take in the worst possible situation. So we need to talk about this input size business. So each one of these, you can think of it like an input string, which is consisting of a bunch of zeros and ones, and then your computer would interpret what those bits mean. So I'm not going to go into too much detail on that, because we're not going to need to go that far. Like I said, I'm going to keep things a little bit higher level, because we really care about talking about solving problems, not the fundamental natures of computation itself. That would be dedicated to a class like 355 or 356, where you might get this at the beginning aspects of those types of things. Let's talk about input size. So the big thing is that each problem defines a problem instance each with its own size. And I'll use size in quotation marks because it makes it fun. Now, more formally, so this is the formal aspect of input size. We're going to find in this course we're not going to really worry too much about that. It'll pop up in more things you might encounter in later CS classes. In this class, we're not going to really encounter this very nuanced, neat way of looking at input size, but I'm going to give you some examples regardless. More formally, input size is determined by how many bits, and like I said, the little caveat is that it's some and any other reasonable encoding scheme. Just as a fun little aside, probably most reasonable encoding schemes that relate to binary will be sufficient. Things like unary, that's where you just have ticks. That's not a good and reasonable encoding scheme. If you're interested more in that kind of stuff, the third and fourth year possible algorithms classes usually get into those kind of details. It's very interesting. Now, how many bits are required to encode an instance of a problem? The big takeaway here is that typically, the larger the input size is, the longer the algorithm, I'll just abbreviate algorithm with alg. The algorithm takes to run in the worst case, which I'll define more carefully in a bit. So So the big thing I want to point out is that we're going to consider reasonable considerations of what the input size is. Sometimes you'll find that this formal definition, we don't really have to worry too much about it, but you'll find that in this class it should be rather intuitive. We measure complexity, which I'll define that in a bit, possibly for our next class. We measure complexity with respect to what is being considered the input size. So I'm going to give you some examples about this because I find that at first it sounds a little strange, but it really does make sense once you actually kind of pin it down a little bit. And I'll give you enough of a justification of why this matters. Some examples of reasonable considerations of the input size include, I'm going to give you some examples because I find very often students get a little hung up on the idea of input size. So I'm quickly going to run through some examples, then I think we'll pick things up after that with algorithms in the next class. To sort an array A of length n, the input size is n. Now, in this circumstance, it's quite normal to measure the input size in the number of items because the numbers, you want to think about the numbers in the array just like if they were a fixed number of bits. So imagine I give you an array. Each one of those numbers is going to be encoded with a fixed number of bits that will be of sufficient size that my machine is able to interpret them as a word on the machine. Now, if you're not sure what I mean by a word, I mean in the computer system's way of a word. If you're not too worried about that, just don't worry. Just basically just assume that these array A, the numbers in there, you can think of them like some fixed number of bits. Because I can take my problem instances and assume that my machine is capable of reading in what one of these numbers looks like. So to traverse the binary 3T, the input size is the number of nodes in the tree, right? Pretty straightforward, right? I have a bunch of nodes, each with keys or possibly some it has a key in it and some references. You'll find that the input size is in terms of the number of nodes in the tree. Now, I must stress that if you really want to get really picky about the input size and you want to be very particular about how you measure the input size, you could technically go through each one of my numbers in the array A or my nodes and look at the numbers and you can ask the question, how many bits does it take to encode an integer? Well, you might know this, it's roughly logarithmic. So I'm just going to give a few. I'll give one more example of something you might encounter. So multiplying two matrices. Multiplying two matrices has input size of the dimensions of the matrices. I give you two matrices. I want to multiply them. The input size would be the dimension. So if I give you a n by n or n by m matrix, and I give you another one of sufficient dimensions such that I can multiply them, it'd be measured in the dimension of the result. Well, it would be the dimensions of the two matrices. If you know a little bit about linear algebra, you know that the dimensions of two matrices are related to one another. Now, this is going to be a little different. Sometimes you actually really have to care about the input size sometimes. You might use a bit more of an accurate measurement of what the input size is. So in a lot of practical circumstances, these will be basically perfectly fine because that's normally how we do things, right? I store a bunch of ints. So for my integers, I just use ints. I might use for floating point, like double. It's very intuitive. This last case, I just want to be a little bit clear that this is where if I want to get really anal about the input size, so determining if a number is prime may have input size of the number of bits required to represent the number. So you might naturally ask, Dan, why is that the case? Well, it's because in cases like this, the parameter will be the integer itself, where you have to imagine, okay, well, how do I exactly process an integer like this? Well, normally algorithms will be measured with respect to a logarithmic number of bits in these number theoretic algorithms very often. So you have to be a little bit more particular when you're doing your analysis. Because unlike where we think about, oh, it's n, where n is the length of the array, that array is encoded with a bunch of numbers, right? So the input size there makes sense. You can think of each one of those numbers as some fixed number of bits that you've read in that array, because you're given an array. So just in contrast, so I'll just give you an explanation. Okay, so each one of those elements in the array, they're usually encoded with some number of bits, right? So how much does it take to encode, say, 16 bits? Well, that's some constant number, right? In contrast, you might have to be more particular with the integers because here, the integers might get really big, right? Here, we might want to get more anal if you were making certain assumptions about the sizes of these. But in our machine model that we're going to use, we're just going to assume that you can actually fit the numbers in. Regardless, if that case applies for all of these, however, when you're measuring the efficiency of an algorithm, you'll find that you have to be a bit more particular about the input size sometimes. So technically, these first three would be, if you're extremely anal about measuring the input size, would be considered somewhat inaccurate, but are perfectly fine to do because, remember, we can treat the numbers like they're a fixed or a constant number of bits, each one. Okay? So sometimes we'll care about the magnitudes of the numbers, like in this case. That's when you get a bit more anal about the input size. In these cases, we care about the number of items, okay? So the big thing I want you to take away from this beyond that, so just remember, if you're getting a little lost on this idea, just watch this again. But remember, it's nothing too complicated. You've encountered this before. So just remember, for any problem, you need to specify the input size. And it must be done appropriately. and it must be done appropriately. Okay. Anyways, we're going to stop right here. I want to say thank you very much and have yourself a beautiful day. I'll see you in a bit.